Alrighty, nerds. We are going to go ahead and finish up yesterday's notes. And in yesterday's notes, we built all the way up to this amazing property of logarithms called the change of base formula that allows us to change the base of a logarithm to any base that we would like. Here we solved 2 to the x equals 6 4 different ways. Base 2, base 10, base e, base whatever you wanted, which means all 4 of these things are exactly the same. Change of base does a lot of neat stuff for us, but one of the things it allows us to do is type on a calculator. So we can actually evaluate a logarithm now on a calculator like this that doesn't have a log base function on it. And it doesn't matter if we do it with log base 10 or log base e, it won't make a difference. So we practice, first and foremost, simple evaluating on a calculator. Green feels good. I'm going to write in green. Somebody let me know. Log or ln? ln. Someone said ln first. So let's use the natural log to evaluate this. It doesn't matter. You know what? I'm going to write them both. Log base 3 of 12 is log of 12 divided by log of 3, which is the same as the ln of 12 divided by the ln of 3. It won't make a difference. Either way, you get the same result. I'll type this one just because someone said ln first. Just make sure you're closing your argument. If you don't close your argument, the calculator doesn't know that the logarithm has come to an end. 2.262. Okay, there it is. That easy. 2.262. On the homework, 2.262. It says to write the fraction you used to evaluate your logarithm. So I would expect you to write one of these two and then what it equals. Boom. This one. There is nothing new about this. It's going to be done exactly the same way. It doesn't matter if you choose log or natural log. Base on bottom. I'll use the common log for this one. Just make sure I close my argument. And you don't even have to type 0.5 because it opened a set of parentheses for you. You can actually do 1 divided by 2. You don't even have to think. Close parentheses and boom. Negative 3.459. Did I go to? Yeah, 3 decimals. Negative 3.459. But I do want to highlight something else about this statement. It doesn't matter. Notice that both of these have a, bless you, notice that both of these have a fraction in their denominator, specifically a reciprocal of a whole number. Yes? Can we agree that the number 1/2 is 2 to the negative 1? Yeah? So check this out. I'm going to take, it doesn't matter which one. I guess I'll just do this one since it's the one I typed on the calculator. And up here, I'm going to write log of 11 over log of 2 to the negative 1. And the reason why I wanted to do that is because I can take this negative 1 out of the exponent position of this argument down here and move it to the front. If there's a negative sign anywhere in a fraction, in the numerator, in the denominator, or simply in the front, they all mean the same thing. It's a negative version of that fraction. So you could write it like this. And if you undo the change of base, meaning write this as a single logarithm, base on bottom, see, the change of base rule allows us to see things like this are true. That turning the base of the logarithm over, reciprocating the logarithm's base, is the same as if you had just put a negative sign on the front. And that's the same result as reciprocating the argument, but that's something we've seen done before. Well, yeah, it doesn't matter if you reciprocate the argument or reciprocate the base. Either way, it puts a negative sign on the front. So if I were to evaluate this, I am going to get this back. This is a pretty nifty trick. Makes a lot of questions easier to look at as far as their answers are concerned. And so why bother? Why bother making a point of telling you that? Well, those of you that have been with me this whole year, which is almost all of you, hopefully you've come to realize the kind of mathematician and educator I am. If I put extra credit on a test, it'll always be an understanding style question. And there is nothing more important to understand about logarithms than the change of base formula. So you can pretty much guarantee if there's extra credit on your upcoming test, it'll be involving change of base and having a deep understanding of how it works. Just letting you know if you haven't quite figured those kinds of things out yet. But anyway, that's all you had to do, but hey, knowledge is like Jell-O. There's always room for more, okay? Nobody even... It's not even a joke. Do you guys know that that's like the saying for Jell-O? There's always room for Jell-O? It's not a joke. That's the saying.
I like Jell-O.
Okay. All right. Well, okay. Hey, anyway, yeah. So, earthquakes. We've talked about earthquakes before, but I gave you a different equation for earthquake energy and magnitude. That's because the equation that we worked with in the previous lesson involved energy as ergs. This is the formula when energy is joules, okay, which is a more widely used unit of measure for energy, joules. The energy released by an earthquake is related to the Richter scale using this equation, log of E equals 11.8 plus 1.5 m, where E is the energy released in joules and m is the magnitude of the earthquake. We want to know how much energy a 7.2 earthquake releases. So I just need to know where in this formula does 7.2 go? M. Yeah, it's the magnitude. It's m. All right, what's a good color? Purple. No, I use that. Orange. Let's use orange. Log of the energy released is 11.8 plus 1.5 times 7.2. Grab my calculator, figure out what that is. 11.8 plus 1.5 times 7.2 is 22.6. There. It's not written. But what is the base of this logarithm? Lots of people, please, please, please. 10. Okay. Not as resounding as I was hoping it would be, but yes, this is log base 10. So I'm clearly going to cancel it with exponential base 10. Go Gators, orange and blue. The energy released by this magnitude 7.2 earthquake is 10 raised to the 22.6. But you know what? Answers like this are typically given in scientific notation, so that's what we're going to do. So grab a calculator and we figure out what 10 to the 22.6 is. Let's take that out to 2 decimals, so 3.98 times 10 to the 22nd power. There it is. It's a lot of energy. So scientific notation. You may have noticed in previous math or science classes that scientific notation always has a times 10 to a power at the end. But did you ever realize it's because our number system is base 10, and that's why we have a 10 in our scientific notation? Probably not, right? Well, there it is. 3.98 times 10 to the 22 joules. That's a lot. Questions, comments, concerns so far? Are we ready to rock and roll? Yes, ma'am?
Why did you use the log at the beginning?
Well, it's just from the equation.
Oh, okay.
Yeah, no, that's just the equation from it. How they got that equation, I don't know. But yeah, just pull it right out of the word problem. You don't have to have that memorized or anything like that. So right now what I'm trying to get you to do is just know how to manipulate your equations using exponential bases and logarithms. How about carbon dating? The half-life of radioactive carbon-14 is known to be 5,730 years. Scientists use this fact to estimate the age of artifacts. The amount of carbon-14 remaining in a sample can be modeled using this equation. Again, I don't need you to have this memorized, I just need you to be able to use it. Where A is what you have now, P is your starting amount, and T is time in years. So that is the half-life formula, or one of the half-life formulas for carbon-14. When researchers tested a bowl found in an archaeological dig site, they found that it only contained 1.2% of the carbon-14 that it should have had when they started. So it's how much it started with. We can use that fact to determine the relative age of the bowl. We'll round it to the nearest whole year. And just so you know, because I'm a nerd and I like to give nerd knowledge, carbon dating is only really reliable up to 60,000 years. Why? I don't know, but that's what I saw when I Googled the half-life of carbon-14 to write this question for you. Just so you know. Anyway, let's make it happen. Did I tell you how much you started with? I didn't, did I? And for that matter, I actually didn't tell you how much you ended with. I did, however, give you a percent of what you ended with. So you could approach this the super math theory way and say that you started with P and then say what is 1.2% of P. And that's what I did with first period. And you know what? It kind of fell flat. They didn't really get a full understanding of what I was doing. So why don't I have you do it the same way that I did it when I was in your shoes? If you don't know how much you start with, it must mean that it doesn't matter. So make up a starting amount. And since we're dealing with percents, what's a really easy amount to start with? 100. Somebody said it. 100. Because what's 5% of 100? 5. What's 1.2% of 100? 1.2. You see, since I didn't tell you how much you started with, you can make up any number you want. Heck, you could have said you started with 1. It doesn't matter. And in period 1, what I showed them was this. I said, okay, well, starting amount was P. Ending amount. It says 1.2% of P. But you would have to understand what the word of means in mathematics. What does that tell you to do if it says of? Multiply. So this would be 1.2% of your starting amount. So I set it up like this for them. And I started the word problem with a P here and a not 1.2 because that's percent, obviously. You'd have to convert that to its decimal point right there. And it didn't really work very well for people. So I said, fine, make up an amount. So we're going to make up the amount 100. And what is 1.2% of 100? 1.2. And you're about to see why the starting amount doesn't matter. Let's set up our equation. So we're trying to solve for t. What's the first thing you're going to have to do as far as isolating this variable and using SADMEP is? Say it louder for me. Yeah, you. Divide. You're going to have to divide both sides by 100. You're going to have to divide both sides by the starting amount. And look what happens when you divide by that starting amount. Oh, look, 1.2%. So it actually didn't matter. If I had written, instead of 100, I wrote a p here, and instead of 1.2, I wrote 0.012p, which is what this is. This is 0.012p. The very first thing you would have done is divided both sides by the letter p, and it would have canceled off on both sides, and you would have been left with this. So no, it doesn't matter how much you start with. When you're talking about percents that remain and talking about exponential growth and decay, it never matters, because the time it takes to reach 12% is always going to be the same time, regardless of how much you started with when you know the rate. Anyway, what are we going to do now? Because we're trying to solve for t, and t is stuck in the exponent position. And keep in mind which notes we're in right now, and also that we want to be able to type this on a calculator. So what are we going to do? What can I do? I could use log. I could take the common log of both sides, or I could take the natural log of both sides. It doesn't matter. And the reason why it doesn't matter is because simply by putting a log of any base you want, specifically on the right side, is going to allow you to take the exponent out of the argument and move it to the front as a multiplier. But Ali said use common log, so I'm going to go ahead and use common log on both sides. All right, so I've got log of 0.012 on the left, and on the right, the whole purpose of using a logarithm was to get this fractional exponent out of the argument, to bring it down to the front. So you can't move it down to the front until you have a logarithm. Now what? Trying to get t by itself. What's next? What are we going to do? Which one? It doesn't matter. Pick one. What do you guys want to do? What? 13,000. I don't know what he's talking about. So will someone please tell me what to do next? Multiply by 5,730? Sure, let's do that. Let's multiply both sides by 5,730. I don't know why this is so painful, you guys. Come on. You act like you're not honor students. Last step, please. Someone please tell me how to get t alone. You guys are killing me. Divide by this crap. You just need to divide. This is a multiplication. You're going to cancel it by dividing both sides by that number, whatever it is. All right. I should have been a dentist, the number of teeth I pull. 5,730 log of 0.012 divided by log of 1/2. I think it's important to note, or at least beneficial to note, that in period 1, Michael E., I'm assuming his last name is pronounced Euchre. Okay, Michael Euchre said, could we make this a 2 and make this exponent negative? And I said, sure. So that's what we did, because a negative exponent would flip the base over. So in our answer in first period, I didn't have log of 1/2. Instead, what I had was a negative up here, and this said log of 2. But it's the same result, because like we said up here, this 1/2 could have been thought of as 2 to the negative 1, which moves the negative. And it doesn't matter if the negative sign is on the top of the fraction or the bottom of a fraction. 100% does not matter. But we could type this on our calculator exactly as it sits, and we're going to round to the nearest whole year. Let's see what we get. 5730 log of 0.012, close your parentheses, divide by log of 1 divided by 2, close parentheses, and we get our answer. About 36,562 years. Because it did say to round to the nearest whole year, so there it is. And if that Google website can be believed, this is well within 60,000 years, so a trustworthy number.
Did you make this formula?
I always make up all the problems. I don't use the textbook problems.
Where did you come up with this?
My brain. I've been teaching for a long time. Now, sometimes I'll use the questions from the book for inspiration, but I never use their exact examples. So I'll change the numbers to make it my own question. That way, when we stop using this book in a few years, because we never use the same book more than 5 years, I can still use my examples without doing any copyright infringing. Because they're mine now. Because I changed the important part. Ta-da! Also, I changed the questions that way if you wanted to go look in the textbook for extra practice, you could actually look at the notes that are completed in the book, and it'll be a different question. Right? Okay. Questions on this stuff before I flip the page over? Nada? Okay. Well, because it's an archaeological dig site. That's why. Newton's law of cooling. In case you didn't know it, things cool and heat exponentially. And since there's an E, it's continuous. Okay? And it's the how long it takes something to get hot or get cold is determined by its starting temperature and the temperature of the air or water or oil around it. So we would call that the surrounding medium. So we're looking at this formula and we're seeing lots of T's. A capital T is a temperature. Lowercase t is time in minutes. T sub m is the temperature of the surrounding medium. So this again would be the air or the water or the oil. And again, this can be used for heating or cooling. T sub 0 is the temperature when no time has gone by. That means the original temperature. We already said what Tm is. We know that lowercase t is time in minutes. We know that E is not a variable, that's a number. K is the only other variable that we have here, and it would be the cooling or heating factor of the object, and that just means a known rate at which this substance can cool or heat up. Okay? I need you to know this formula. I'm kidding. I need you to know how to use it. If I need you to use the formula, I will give you the formula. Okay? This is not a physics course. This is not a chemistry class. This is not a physical science class. I'm not going to make you memorize Newton's law of cooling. I need you to know how to use it. Alrighty. Hey, what? If it's on the test, I will give you the formula. You don't. What's the problem? What does she not know?
No, I said I don't want to.
Why?
Complicated.
What's complicated about it? A lot of letters. You know what has a lot of letters? My grade book. And it would be great if all of those letters were the same letter. A. Yeah, me too. But, you know, it's probably not. Probably because people would rather complain about the math instead of just buckling down and doing the math. Anyway, I just told you what all these letters stand for. So you'll be okay. We use Newton's law of cooling to find out how long it takes your tears to cool down my desk when they hit. Okay. A hard-boiled egg at temperature 96 degrees Celsius, which is near boiling temperature of water in Celsius, is placed in 16 degrees Celsius water to cool. 16 degrees Celsius is, if I can trust the student that I have in first period that spent a portion of her life in Germany, maybe a little chilly, she said. Okay. It is known that the cooling factor of a hard-boiled egg is approximately 0.2537. So that is K. We're going to use Newton's law of cooling to determine how long it takes for the egg to cool down to 20 degrees Celsius, which I can only assume is a comfortable food temperature. Round to 2 decimals. 20 degrees Celsius is cold? Is it?
Yeah.
Okay, well, we're going to pause the video and look it up now. I don't know. We got it. No, it wasn't on video. I had it paused. Let's say we got to get this train back on the rails. Man, these students, nobody dies and hides hard-boiled eggs anymore for Easter. I am astounded. I'm too far removed from childhood, I guess. What were we doing? Math. We were doing math. Okay, look. We're trying to figure out what little t is in this formula. We know that the temperature at the end of cooling is 20 degrees. We know that the temperature of the surrounding medium is the nice cool water at 16 degrees. We know that the original temperature of this egg was a very hot 96 degrees. All this is in Celsius, of course. And lastly, the question tells us what the cooling factor is, and it was 0.2537. All right. 68 degrees Fahrenheit when I paused the video. That's what we found that to be. 68 degrees. That's 68 degrees. Because we were curious, right? So this is hotter than 68 degrees. Oh, this is 68. So yeah, that's a little chilly then. Well, I still got it open on Google. Let's check. 16. Just under 61. Just under 61. Anyway, let's fill out Newton's law of cooling and solve for T. 20 equals 16 plus 96 minus 16 e to the negative 0.2537 t. And we have one variable and we're trying to solve for little t. Very, very easy. What are we going to do first? That's the real question. Subtract 16 from 96 or for both sides? Do both. Eventually, yes, we are going to do both. So let's go ahead and clean this up like PEMDAS tells us, just because we can clean this up. Let's clean this up. But Allie, you're right. We are going to subtract 16 from both sides in just a second. But before I do that, I want to make a point about something. The next step is going to be subtract 16 from both sides. You cannot ever, ever, ever try to add this 16 and this 80. They're not like terms because this one has a variable expression sitting next to it. It's like this says 16 plus 80x. You can't add them. And if you could add them, there would be absolutely no point in subtracting the 16 here if you were just going to add it again here. And even though I've said that, I'm still going to have some students add those two numbers if I put this on my test. Please don't do that. You can't do that, okay? I have IB students that do that every year. Please don't do that. You can't do that. But Allie said subtract 16, and she's right. I'm going to subtract 16 from both sides. We have 4 equals 80e to this negative 0.2537t. What's up? Yep, that's what we're going to do. We're going to divide by 80 now. Because it's sitting in front of an exponential base, we're going to divide both sides by 80. Please don't touch a calculator. We don't need a calculator until the very, very end. Because we don't care what this fraction equals. We're just going to type it as a fraction on our calculator. Well, actually as a division on our calculator. We're not even going to think. We're not going to touch that calculator to the bitter end. So my variable t is hanging out above an exponential base e. Wouldn't it be great if that e wasn't there? What am I going to use to cancel e? Which one? What cancels exponential base e? ln. The natural log. And the reason why is because ln is log base e. So we're going to use log base e to cancel exponential base e. But instead of saying or writing log base e, we just use shorthand and write ln. Okay? Could we use the common log? Absolutely. But it wouldn't cancel the e. It would give us a log of e in our equation. And there's nothing wrong with that. It's just more work. I'd rather cancel exponential base e because that's what the natural log does. Again, I don't care what 4 over 80 is, even though it's a pretty decimal. What if it wasn't a pretty decimal, right? What if it was really, really bad, like 4/71 or something horrible like that, okay? And in case it's an ugly fraction, do yourself a favor, just leave it like this. Let the calculator do the heavy lifting, okay? Because this is finished when you divide both sides by that negative decimal. So t is this, whatever that is. Natural log, 4 divided by 80. Make sure you close the argument so the calculator knows that you're done filling in the logarithm. Divide by this decimal, negative 0.2537, and hit equals. I think the directions say, yeah, 2 decimals, so about 11.81 minutes. And there it is. Again, if I want you to use Newton's law of cooling, I will give you the equation. So please don't panic. That is it, nerds.